I'm Maria. I'm going to talk about the impossibility of a universal work extractor from coherence. And I work at Oxford Quantum Circuits, a quantum computing company. But I did this work during my PhD, which was on quantum thermodynamics in collaboration with student Sam Plesnik. So my, does this work? Right. Okay. I don't have USB, but I'll just click. Right. Okay. Oops. Okay. Cool. Cool. Yeah, so the PhD themes were kind of quantum thermodynamics and quantum foundations, and I now work on quantum error correction, and the company is building quantum computers from superconducting qubits, so happy to chat about the energetics of those topics later if you're interested. But this will be a more quantum thermodynamics-focused talk. So to give an overview of what I'll talk about, I'll start by talking about some of the results to do with extracting work from coherence, and you'll see there's this kind of back and forth story about how useful coherence can be for work extraction. Then I'm going to compare some different approaches to understanding how we can extract work from coherence. One is an approach from resource theories and looking at explicit quantum dynamics, trying to understand the resources that go into doing a work extraction task. And another is from a theory called constructor theory, which has a different approach to thermodynamics and to physics more generally. And at the end, I'll introduce a kind of novel connection between some of the ideas I've been looking at in the constructor theory of thermodynamics and this kind of quantum protocol for extracting work from coherence that I'm comparing to. So to start with, extracting work from coherence, I'll introduce this kind of story of what's been happening. So here's the setup. The question is, how useful is coherence as a resource? So you can imagine that you have states at two different energies, and then you have a superposition of these energy states, and that is a coherent state, and then you can imagine an incoherent version of that state where there's the same kind of weighting of those two energies, so the overall energy is the same, but it doesn't have the coherence. And then there's the question of, is there a difference in the usefulness of this coherent state of energy superposition compared to the mixture? And one difference is that the coherent superposition has more free energy, so you might think that you can make use of this and extract more work from the superposition than you can from the mixture. So an interesting result when people looked into this was a phenomenon called work locking. So what was found is that if you try and extract work from a single coherent state and compare it to the work that you can extract from the corresponding incoherent state, you actually can just extract the same amount of work. So even though you've got more free energy in the coherent one, you can't extract that as extra work. So it's like the work is locked up in the coherent state, so that's why it's called work locking. So that seems a bit sad that you can't get that extra free energy. But then later results introduced a coherent catalyst into the picture. So added a catalyst in, which itself has coherence, and then used this catalyst within the work extraction task. And then it turns out that there is actually a way to now not be constrained by this work locking anymore and extract more free energy from the coherent state by using this catalyst. And the result kind of shows that you can create this sequence of thermal machines which approach this limit of extracting the free energy of the coherent state with a kind of arbitrarily high success rate, low failure probability, and you can keep improving the change in the quality of your catalyst as well. So you can create this sequence of machines approaching that limit. And this is an outline of how that protocol actually works. How do you extract this extra energy and this extra work? So the idea is that you've got these three systems. We have a battery, which is where we're going to, we'll charge it up with the work extracted. We've got the system that we're extracting work from, and the coherent reference, which is what's acting as this coherent catalyst. And then there's three steps. There's pre-processing, which prepares the catalyst and the system into a state that's kind of optimal for this work extraction. Then you have a work extraction step with the system and the battery. And then finally, this repumping step is to get the catalyst back to its original state so that it's really functioning as a catalyst that you can reuse. So now I want to talk about the constructor-theoretic theorem, and then I'll bring it back to connecting it with this protocol in the next section. So briefly, the idea of this theory, constructor theory, is to formulate laws of physics in terms of what can and can't be made to happen to a system rather than what will happen to a system. And it's kind of inspired by quantum computation and information and thermodynamics, and it aims to unify laws of physics using these principles formulated in a particular way. And the aim is to express laws of physics in terms of tasks that are possible tasks and impossible tasks. And in particular, possible means that a task can be performed in a cycle. And the idea is that these principles kind of constrain your dynamical laws. And ideally, in this kind of full constructor theoretic framework, these principles should be independent of quantum dynamics, scale independent, and also exact in the sense that they're non-probabilistic and they aren't using approximations like coarse graining. And when we say that a task is possible, meaning it can be done in a cycle, that means that a constructor exists for the task. So constructor is like a generalized version of a catalyst, which enables a task to be performed in a cycle. So you can imagine like a chemical catalyst as an example of a constructor. Or if you imagine having some water at some temperature with a stirrer and a battery, and then you use that to power the stirrer to heat the water, then the stirrer is acting as a constructor for this task of increasing the temperature of the water. And you could also imagine that you can have a constructor for scrambling an egg, but you can't have a constructor for unscrambling an egg. And this is an example of kind of irreversibility, that you can do a task in a forwards direction and not in the reverse direction. And that's the idea behind a new kind of irreversibility, a new way of formulating irreversibility based on these principles called constructor-based irreversibility. And the idea here is that a task can be possible within this definition of possible, and the opposite task impossible, even with all the underlying dynamics being reversible and, when applied to quantum theory, unitary. So the constructor-theoretic theorem about work extraction is this. It's that if you can deterministically extract different amounts of work from different systems, then those systems must be perfectly distinguishable. And what's interesting about this, one thing is that it's derived in this scale-independent, dynamics-independent, exact framework, so it's based on these kind of principles about what's possible and impossible. And another interesting thing is that it connects information and work and energy in a different way to the one we're used to, which is Landau's principle about erasing information and connecting that with entropy. And it also is derived using the first law of thermodynamics of energy conservation instead of the second law. And so what are the implications of this for coherence? One of them is, so what you can do is imagine that you have a work extraction machine that can optimally extract work from a coherent state, and then imagine that we put some other input into it and try and extract work from that coherent state as well. So according to this theorem, this one particular machine would only be able to deterministically extract that optimal work from inputs if they are orthogonal, because they have to be perfectly distinguishable. So it can't do it for non-orthogonal inputs. And so this means that a work extractor has to be from coherence has to be a specialized machine rather than a universal machine. And we can now look back at this protocol that I mentioned earlier and see how this all fits together. So the way that this comes into the protocol is that in this pre-processing step, it's actually state dependent. So that step of preparing the system using this catalyst into a nice form for work extraction is, it takes in there's a part of that step which maps the system state to a one state. So it's kind of based on this unitary process of trying to map it close to one. And that's the step that's state dependent because that process needs to know what state is going in for it to work. And so we have this compatibility with the theorem connecting work extraction and distinguishability, because this can only work if the system it can deterministically extract work for states that are orthogonal, but not for any non-orthogonal inputs. So you can see this in a kind of quantum circuit layout. You can invent a quantum circuit that can extract the work for two orthogonal inputs, but for any other input, it won't work for the non-orthogonal inputs. So we have this conclusion that we have these special purpose machines derived in these different ways from the resource theory and constructor theory approaches. And now, as the final part, I want to talk about a kind of extra twist on these ideas with a further connection to some constructor theoretic results, which actually connects back to this irreversibility that I mentioned earlier. So we saw before that there was this trick with the extracting work from coherence, that it seemed like, oh, the work's locked up, and then there's this idea of introducing a coherent catalyst, and suddenly that enables this work to be extracted. So we know that bringing in catalysts or external machines that you can reuse can be very powerful for expanding what tasks can do. So one interesting thing to consider is if you bring in another system, can we make this work extraction machine universal? And there is a system that I've been looking at in a different context called the quantum homogenizer, which takes an arbitrary input, any state, pure, mixed, whatever, and kind of transforms it, maps it to a fixed state. And so we can imagine trying to use this machine to take an arbitrary state and map it to the one state, and then slot that into this pre-processing state-dependent step to actually make a universal machine. So the quantum homogenizer kind of has this input system qubit and then a load of identical reservoir qubits. They interact one by one with the system via this weak partial swap interaction until the system converges arbitrarily close to the reservoir qubit state, and the reservoir qubits have only deteriorated a small amount from that interaction. So it's a kind of candidate for being a constructor and being reused for doing this task. But in the work that I've done looking at constructor-based irreversibility, we found some cases where this machine is a constructor and some where it isn't. In particular, I was looking at the task of turning a maximally mixed state to a pure state versus a pure to a mixed state. And what we find is that in the pure to mixed case, you can build a constructor from this homogenizer, but in the mixed to pure case, you can't build a constructor from this homogenizer. So there's this asymmetry, and that connects to irreversibility, because you could say, well, there's a constructor for pure to mixed. There's no constructor for mixed to pure, even though everything's unitary, reversible dynamics. But what's interesting here is that the task of taking some arbitrary state to the one state maps onto the mixed to pure task, which is the one that is constructor theoretically impossible using the analysis of a constructor that I've been looking at. So what we find is that there's now two different connections to this quantum protocol for extracting work from coherence. One is this connection with the theorem that connects distinguishability and deterministic work extraction derived in this scale-independent, dynamics-independent, information-theoretic way from constructor theory. And then there's this other connection with the explicit qubit model for a constructor with the homogenizer for mapping a mixed state to a pure state, not being a constructor, and so that also makes a compatibility with this result in a different way. So I'll just finish up with some of the open questions kind of in this area that follow on from thinking about these ideas. So one of them is that it's interesting that this theorem is about kind of taking these inputs, and it's only if they're perfectly distinguishable that you can do the task, and there's going to be some limitations if you try and make a machine that also works for non-orthogonal inputs. So it'll be interesting to compare this to work that's been done on, in general, looking at quantum information processing with inputs that work for multiple different inputs, even when they're non-orthogonal, and what the extra costs of doing that are. Another aspect is that this theorem that I've mentioned, connecting work and distinguishability, arises from conservation of energy. It'll be interesting to compare it to putting a different conservation law in there and seeing what theorems you can derive an analogous theorem for that based on like a work-like quantity for that conserved quantity, and analyze different conserved quantities. And I'm also working on kind of fleshing out this definition of how you define a constructor using, so the measure that I use at the moment is kind of quite unrelated to measures that people tend to use for these kinds of questions. So I want to connect it with neutral information, and that's something that I'm working on at the moment. And just to summarize quickly, the idea is that constructor theory and resource theory are these kind of different approaches, and they have this intersecting conclusion with the impossibility of a universal work extractor. So it's a nice case study for comparing them. We can derive this impossibility of a universal work extractor in different ways using these approaches. And there's also this connection with the qubit model for a constructor that doesn't work, to also connect with this impossibility of the protocol becoming universal. So thanks for listening. Happy to take questions. This is the paper reference if you want to see the details. And I also make YouTube videos, which I've put there if you want to have a look. And I was inspired by Konstantin's talk to put a Christmas photo of OQC here as well. And if you have questions about OQC, happy to answer them as well. So thanks for listening.
Thank you, Maria. Who has question?
Thank you very much. Very nice talk. With the homogenizer in the circle, so all the qubits have the same state. Mm-hmm. So yeah. Why can't you just make a full swap in one run?
You mean just swap?
Like if you show us the figure, like you had this very nice animation, and it looked like, yes, of course, if you have many qubits and you make partial swap, then like after some time you get what you want. But like it looks like if you just make one full swap, then you have it in like. Yeah. If you make a swap, so the question around that is about you want the candidate constructor to retain the ability to perform the task again. And if you do this kind of one swap, you will be able to do it multiple times, but you'll have this kind of limit of however many qubits you have in your reservoir is going to define how many times you do it. And so you can consider that kind of machine. Yes, okay, that's true, but like here you also see that there is this violet part in the qubit. So like if you do it many times this way, then it looks like you have the same problem, because like with any with the next and next run, you will have more and more violet in the circle. So after many uses of the circle, you would have the same problem as this with the like single swap, no?
Yeah. When I think about that system of swapping, I call it a swap machine. So I think the swap machine kind of has. So when we look at whether it's a constructor, what you want to look at is the kind of convergence properties of what happens as you increase the reservoir size and reuse it lots of times. And the quantity that we use to define kind of the behavior is kind of look at what happens to that quantity in terms of some fidelities of the original state with this state, with the deteriorated state, and the accuracy with which it's able to perform the task. And the kind of complication with trying to, so you could also study this kind of swap machine, try and use this a similar measure to study it, but there's kind of subtleties with how do you define the accuracy with which it's performed the task, as well as the amount that it's deteriorated. And so, it's kind of another model that could be explored, but this one was kind of quite neat because you get this property that the deterioration of the reservoir qubits can be made arbitrarily small by making the coupling strength weak, so you've kind of got a different pathway to trying to make it converge nicely.
Yeah, thanks a lot for the great talk. It's nice to see some more theoretical talks as well. What I was wondering about the relationship between the constructor theory and the resource theory is that from the constructor theory, it seemed to be that you naturally get like these binary results, like whether something's possible or not, whereas in resource theory, you can oftentimes also talk about somehow the resource needed to achieve a task to maybe some fidelity. Is there also like such a resource consideration that can be made within the constructor theory approach?
Yeah, I'd say it's not something that's been done yet. I think the kind of closest thing is kind of this analysis that we've been doing of systems like the homogenizer, trying to kind of construct this quantity to quantify how deteriorated it gets and if it acts like a constructor at that limit. And I guess this idea of trying to express that using neutral information instead is kind of one of the motivations is to try and connect with other quantitative results from a resource theory analysis. But yeah, I think that there is this kind of difference in motivation as well, though, that the motivation in constructor theory is more, at least in the beginning, to have these like binary statements of like if it's possible or not, rather than quantifiable ones, and that's kind of what lets you make these more generalized statements, like having this dynamics independent information theoretic. Dynamics is scale independent. Yeah. So you kind of get that, and then the trade-off is you don't have a quantitative result, but you've got a kind of far-reaching result. So yeah, there's a kind of trade-off.
Yeah, it's very cool. Thanks a lot for the great talk.
Yeah, thanks.